We start Oscail, and in the Ortex folder we can see the VUKRAWXX job. We open this job. The job name is padded to 8 characters with X's, and we save this file in a folder, a new folder we call Pixel. This is to keep Pixel operations separate from other things. And now we open the job in the Pixel folder. Now the first thing we want to do is to extend the hydrogen positions to neutron diffraction values. Do this in the main setup in Ortex by selecting XH Calc. And if you just default through this, reasonable values are set for the hydrogen positions. Now we can close Ortex, and now we can add these positions by using the Pixel dialog. Select Add XH. We need to find the file we've written. It starts with XH, and there it is at the bottom. We've now added them satisfactorily, and the new file is written to the NXH folder. We open it, and now the first thing we do is we do a Centroid scan. Open and close Ortex and then add or activate Centroids. We now have the Centroid. You may or may not see the Centroid. Do a lattice scan for or calculate contacts for this. The default distance is set to 20 angstroms, which is satisfactory. And use all defaults on this, and we now have the lattice scan done. We can deactivate the Centroids now at this point, and now we're ready to run Pixel. Now run Gaussian or Orca to generate the electron density. There are various options. We select the defaults, run Orca, and Orca runs, calculating the electron density. The electron density file, when generated, is passed to Pixel C, which runs automatically, and it starts computing the energies between the molecules in the lattice. And you can see it works through the various interactions in the lattice. And when this is finished, it writes up the lattice energy calculated by Pixel and compares it to the lattice energy calculated by the CLP program. These should not differ greatly. If they do, you need to investigate it further. Now we can look at the results. They're in the NXH folder, and the Pixel output is in this file _sim.mlp. If we edit this file with Notepad and use Control A to select all of it and Control C to copy it to the clipboard and open an Excel spreadsheet and paste the results into the Excel spreadsheet, and now use data text to columns, and we need to use delimited, and on the next we have the option to pick comma. They're comma delimited. Now we can see everything is spread out properly, and if we select the data only and then select sort and sort on the pixel energies, the largest energy contributions or interactions are at the top. There are 4 of them. If we select these 4 symmetry operations, then we can get a picture of them. So the first 4 symmetry operations are the most significant. Control C to copy these, and in Oscail edit the SymOp list. Use Enter a few times to make space at the top of the file and paste in the 4 symmetry operations. If we now run Ortex, the first thing we should do is calculate the hydrogen bonding in the lattice using atom mode, calculate contacts, and we can see that there's a 1D hydrogen bonding motif. If we turn this around, you can see the 1D chain. Now if we clear this and add in the units which we have put in the SIMOP list, add contacts from the SIMOP list, then we see the 4 units added. Now 2 of them are in a stack with the original 55501 molecule, and 2 of them are hydrogen bonded. The stacking is more important for crystal growth than the hydrogen bonding in this case. Now whenever you have a picture in Ortex, you can get an OpenGL picture of the same thing when you exit Ortex. On the Oscail menu, if you click the OpenGL icon or toolbar button, you get an OpenGL rendering of what was in the last Ortex picture. Now, when you exit Ortex, the SIMOPs in the list are written to the GEO file, but also with a translation to conventional form. So you can see here the 4 symmetry operations translated to standard form. I hope you find this useful. There's more details in the Oscail help. The latest paper we published on this in 2021 is there, and you can look at this and you'll see as you scroll down through this paper there are some things you'll recognize from what we've done in the tutorial, and there's the table that we've just looked at. So I hope you find this useful.